Alright, welcome back. So we're going to finish up these slides on Boolean algebra in this lecture, and let us get right on into it. So remember that it's just logic all over again, it's just slightly different notation, okay? That's what Boolean algebra is all about. And so we ended last time just converting stuff using our table of things that is exactly the same from the logic lecture, which is fun. Just looks weird, or maybe familiar, in fact. And this is where we left off. And forgive me if I said that I have talked about this before, because I probably didn't, and that was CSCI 1 and I was dreaming, but maybe I hinted at it. The idea of functional completeness, the fact that you only need and or not. Let me show all this to you, okay? So, a bunch of operations in Boolean logic, it's said to be functionally complete. Complete is the key term here. If you can make any Boolean function, like you write me a table, you give me some zeros and ones, I can give you back the answer no matter what, always, using addition, multiplication, and complement. If I just use these three things with my variables, I will eventually be able to, with a long enough thing, a long enough Boolean formula, I will be able to express whatever function you're asking me to express, okay? Like going back to, which question? Like this, for example. All you needed was and, or, and not. So, addition, multiplication, and complement, it's called functionally complete because it can represent any possible Boolean function, okay? That's all you ever need. You don't need any fancier ones. You don't need XOR, you don't need biconditional, you don't need even implication, because you know how to convert all of that to P implies Q is, that's all equivalent to, maybe I can write this over here, but let's go back to blue. P implies Q, remember, that's just equivalent to not P or Q. The nots and the ors and the ands, they're all the same, okay? So that's what it means to be functionally complete. You don't need anybody else. You just need these three operations on your variables, and you are golden. That is all you ever need to represent any possible function. Any Boolean function. Okay, hopefully that makes sense. It's a fun little property, and people back in the day, they asked, like, is this the right answer? Like, is this good enough for us? And the answer is no, because you can do fancier things with fancier operations. Okay? Circuit designers, they love NAND and NOR gates, because they are functionally complete just by themselves, which is really, really fun. So this is NAND, and it's written that way with this up arrow because like the pointy part of the up arrow kind of makes the and sign, and NOR, the or part, the pointy part of the down arrow kind of makes the or sign. Yeah, I guess that's why they chose. I guess that's why they chose that. Let's see here. These are functionally complete just by themselves. So you take just NAND gates only, you can represent any possible Boolean function. I'm not going to prove it to you, but it's really, really fun. I hope your book talks about it slightly more. I'm not going to like waste too much time on it, but it's a really, really fun property no matter what. No matter what fancy, long logic operation, function, whatever it is, you can just make a bunch of NAND gates. You can NAND together P and Q and Z and Q in a fancy enough way that you will have that original function. Okay? It will all work out. The right-hand side will always be the same. So NAND is defined to be first do and, then not it. Okay? That's the idea. It's like the not is on the outside, and then the and's in the middle. That's why it's in that order. It's not like and or something. It's NAND, so you do the and then the not. And apparently, that by itself, if you just use this one operation, define that to be your basic operation. Or that's a very interesting one, right? Just define that. You can make anything else, okay? NAND by itself is functionally complete, which is very interesting to think about. You can make or, you can make and, you can make negation very easily. Let me show you how to make negation. So, not x, that's equivalent to not x and x, yes? So, not x is therefore equivalent to x NAND x. You see that? This is just the second x goes away, and then they negated the thing. So you can make every possible thing. You can make x or y, x and y. It doesn't matter. Here's one of them. Okay, so that's fun to think about. Same for NOR. Okay, NOR is the opposite. It's first you do OR, then you not it. So x NOR y is first do x or y, and then take the negation. That looks like this. It's again a dual kind of thing, which is fun. And it also by itself. So you can pick as the circuit designer. I'm just gonna use a bunch of ands to make NANDs to make everything, or I'm just gonna use a bunch of NORs to make everything. And that's glorious. You can make whatever you want. Just pick, I want to use NANDs or I want to use NORs. Okay. And this is why I told you to think about the NOT gate as having that circle bit be the part that negates it, because this is how you draw a NAND gate. You draw the AND and then the NOT right after it. Okay, first it's doing the AND and then it's negating. First it's doing the AND and then it's negating. And same for NOR. It's OR and then the little NOT part. Okay, so yeah, what's the point of any of this? Like, why did we think about this? Why do we need it? Circuits, when we make them in our computers, we like to use just a bunch of the same gate. Okay. Because then you just have to get really good at making NAND gates, for example. And you can buy those in bulk, right? That is the point. We like to save money as circuit designers, okay? So the fewer number of operations that we have to do, if we can simplify whatever our functions are, that's great. And if we can make it so that we only need one kind of gate that we ever need, that's even better, okay? Buying in bulk is very, very nice. Okay. So now for a topic that you already know about. Okay, I'm just going to talk about it a little bit more thoroughly. So Boolean satisfiability is the idea of I have some Boolean formula f of like x, y, z. Maybe it's, I don't know, x and y or z bar or something like that. And we want to figure out, for some reason, we care about when this Boolean function returns back true when we give values for x and for y and for z. Okay, that's the hope, and we've made a fancy term to mean gives back true. We call it satisfiable. Okay, a Boolean expression, it's satisfiable if there is some way, any way at all, of manipulating the values of the input variables, x, y, and z, that makes that expression evaluate to 1, so true. We want true back. We like true things. Okay, so now the fun part is the program that you implemented executes in exponential time. Okay, that's 2 to the n, where n is the number of input variables. That was the running time of your sat-solve function. Okay, believe it or not, it was horrible. It's a horrible, horrible runtime. And let's talk about computability theory. You'll read about this a bit more in your book, and I encourage you to read it in depth, but this is as far as I want to go here in lecture. Let's get rid of that. If you want to determine whether or not a formula is satisfiable, and that's an arbitrary CNF formula, because you know if you have a DNF formula like this, it's very easy to figure out when it's satisfiable. Okay, it's like, okay, here's one solution right here. X is true and Y is true. CNF, on the other hand, that's a lot harder. An arbitrary CNF formula to determine whether or not that is satisfiable. It's what's called NP-complete. It's a problem that is in this set of other problems. It's a set of very hard problems, okay? NP-completeness. The set of all problems that are NP-complete, we say. And at this point in your computer science career, it's enough to say that this just means it's really, really hard to solve, okay? The best algorithms that we know for anything, any problem that is in this NP-complete set, and Boolean satisfiability is one of them, they take exponential time, okay? In the best case. So that is, I guess in the worst case, that is the point. You can never solve every problem any better unless we find a nice trick, okay? And you might have heard NP, you might have heard it with P, this problem, P equals NP, maybe. And I guess it's my turn to tell you what that means. So just think of them as clouds. Okay, P is a bunch of problems, and NP is a bunch of problems. And these are like easy problems in P. They're like polynomial time, very easy to solve. So anything like O of n squared, a bunch of problems that are those time complexities are in P, and then NP are harder problems. They're what's called verifiable in polynomial time, and I don't want to get into what that means. But the question is, these hard problems, is there any overlap? Like, can we do this? Is that a thing? Is there something here? That's the question. And if there is, that means P equals NP. If we can bridge the gap, we can get to anywhere else. Okay? Because we have this concept of NP completeness. And I know I'm just throwing a bunch of terms at you, but when you get into your computability theory class in upper division, you will now at least have heard these words once before. Okay? So the idea is we can't do much better. We can't do any better than exponential time unless P happens to be equal to NP. Okay? That's the idea. If that's the case, there's a fancy trick that nobody's been able to come up with yet that will solve Boolean satisfiability very fast, and our lives will become very much better. I can promise you that if P equals NP. All these problems that were really, really hard are now immediately, easily solvable, though it might ruin some cryptography stuff. It might be harder for us to log in on our banks. We'll deal with that when it happens, okay? If it happens. Probably won't. So tic-tac-toe is my example of Boolean satisfiability for you. So what I'd like to do is encode for you the question, what ways are there for x to win, as a Boolean formula, if you can believe it. There is a way to do that. So take this game board, we're going to represent it in a special way. We're going to say the game board for tic-tac-toe, it looks like this. It is B11, B12, B13. That's every state of the game board in the first row, and of course B11 can be X or O. Those are your possibilities. Okay, it's either an X or an O. Maybe that's a slash is a better thing to use. So every B can be X or O, because that's tic-tac-toe. That's 2-3, B3-1, B3-2, B3-3. Okay, so that's how we're going to represent our game board in terms of logical variables, and you can represent the game board itself in logic by saying, okay, it's a 1 if it's X, it's a 0 if it's O, things like that. Okay, so we're going to talk about this. Don't worry. We're trying to ask the question, what ways are there for X to win? Because if we find a satisfying solution, we'll have one way for X to go and win the game. Okay, that's the idea, and we can keep on asking this question to a sat solver, saying, okay, I want the next solution, I want the next solution. And then we'll come up with all the possible ways for X to win on this game board. Okay? So now, this is a fun little exercise, I think. We have to represent what it looks like, what the board looks like when the game is over in X1. Okay? That's the idea. We need to represent, what the board looks like when the game is over and X1. Okay, so here's how we can do it. We can represent it in logic. I'm going to go back to pure logic now with the normal signs that we know. So for every square in the game board, we have to make sure that the game is over. So everybody's filled in somewhere. Okay, so there's an X here or an O here. There's an X here or an O here. There's an X here or an O here. We can't have any blank spaces. Okay, so we can assert that this is true. We can say, okay, sat solver, this is one of the requirements for the game being over. Okay, every square better be filled with an X or with an O. So for every square, the square equals X or the square equals O. And we can define 1 to be X and 0 to be O if we wanted to, and that gets a little bit closer to logic. But the sat solver will do the rest. It will convert it down to pure logic. I can promise you that. Okay, and then we need to represent the fact that x went first. Okay, we're going to pretend, without loss of generality, we'll pretend that x always goes first in tic-tac-toe. And we're trying to figure out what ways are there for the person who goes first to win. That's the idea. So if x went first, there is an odd number here. So that means there's one more square filled by x than by O. Okay, we need to represent that in logic now. So maybe if we had a function called count x, count all the x's in the game board, and you just give the rest of the game board, we need to make sure that the number of x's on our board better be 5. Like, here's a potential way for x to win, just like that, right? And then the rest of this needs to be filled in with a proper game. Like maybe x went first there, and then O went first here, x went first there, then O went first here, and we need to fill this up. So the game needs to be over, and the board needs to be filled in. So maybe, I don't know, x went here, O can't go here, maybe O went here, then x went here, x went here, game's still not over, O went here, and then x went here. How about that? So that's one way that the game could end with the full board. Okay, that's the idea. And so we'll count x and make sure that it is 5, because if you go first, you're filling the board in 5 times. The person who goes second only gets 4 chances at filling things in. Okay, so that's another thing we have to encode, which is fun. And this is really hard, like adding things, counting, checking if something's equal to something else, and then adding it to some sum. That's really hard to encode in terms of and or not, but I'm going to show you at the end of these slides that it is possible. Okay, but you can just take it for granted that the sat solver is going to handle that for us. We're going to make sure that that's 5. And we also need to encode the fact that x won and O didn't, because technically you can have a game board that looks like this: x, 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 O, 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 yeah? And then this can be random stuff, x, O, x, whatever. Then they both won, right? We don't like that. That's not a valid game board for the end of the game. We don't like that right there. So we have to encode the fact that x won and O didn't. So to encode that x won, we have to make sure that at least one of the ways to win is covered by x. Like maybe all these are the same. So that's one way to encode it. Or maybe x won the second row. That's another way to encode this. Maybe they won the third row. We have to OR together all of these possibilities because x won somehow. Okay? Maybe it was that one, or that one, or that one, or that one, or that one. We have to check all of these combinations of rows to make sure that x won, and we have to negate it for O to make sure that O never won any of the possible ways of winning. None of these worked out for O. There are no matches for all of those. Okay? So that is the idea. We can encode this. We can give it to a sat solver, and it can tell us a satisfying solution. Okay, so let me show you. There is a sat solver made by Microsoft. It's a very fancy thing that people outside of like research don't really use a whole lot, but it's very popular among the people who care. It's called Z3, and let me take you to a website that like implements it and lets us use it for free. So this is the website, and here is the program. We can write a Boolean formula as a program in a special programming language called SMTlib, and we can execute it and find a satisfying solution. This is how the real-life sat solvers work. And they use a bunch of tricks to try and get it as far away from exponential time as possible in the easier cases. Okay, and so here is the program that implements all of these rules. And it's very small, so I'm going to paste it here, and then I'll also paste it over here in our code from class. So let's call it tic-tac-toe.smt2. That's the programming language. Okay, so I'll paste it now if it wants to go. And this is quite large, so let's see if I can do that. Yes, yes, yes. And let's save. Okay, so this is how it's actually a Lisp kind of language, funny enough, that encodes sat solving. And commas are again, or sorry, semicolons are again comments. So we're going to pretend that x is 1 and O is 0 for our encoding of the game being over and x winning. And here are all the ways that we do it. So we're going to declare our variables. We're going to say that b11 is an integer. It could be either 0 or 1. b12 is an integer. b13 is an integer. All of these, 9 of them. Those are the variables that we need to represent our game board with. Okay. And then we need to represent the fact that every square was filled in by x or o. And we assert that. We say that this must be true, sat solver. Make sure that it is in your satisfying solution. So we assert that the count of x equals 5. So here's how you do that. You can make little functions in this language. Here is how you can count x. It's a very silly looking function. ITE stands for if then else. So the first thing is the formula. So if it just so happens that b22 is equal to 1, then give back 1. Otherwise, give back 0. And if we give back 1 whenever it's equal to 1, which we're saying is x, that's going to eventually, with enough if-then-elses, add 1 every time it sees an x, and then sum together how many x's it sees. That's how we can count all the x's. Okay? So checking for equality using if-then-else, which can be encoded in logic. It's kind of similar to an implication, right? So this is doable. You can even encode plus in pure logic, I promise. So that's how you can count x's. And then you can also count o's in the same way, like check if it's a 0, that's our o encoding, and sum together all the ways, all the places we find o in our game board. Okay, and so now it makes sense. Like we got to make sure that five x's are on the board and 4 o's are on the board. Okay, and then we also have to make sure that x won and o did not win. So make sure that 1 won, assert that, and make sure that o did not win. That's the idea. Okay? And so here's my won function that asserts all these things, that figures out if somebody won. It will return true if it did. It makes sure, it checks all the different little cases. Okay? That's what it does. It makes sure, hey, is, oh no, this is kind of, I see what's happening here. The way that it's auto-formatting is just not a nice one. Let's, let's delete, and you know what, we're going to come back in nano if we have to. I'm trying to make this pretty for you. Yeah, I thought something was weird looking. There we go. Exit. Yes, please save. Now back in Vim. Okay, this looks so much better. Sorry. I promise I programmed it like this in a nice clean way. And so here's how you check if somebody won. You check all the rows, like x1, this player that you're passing along won if they won the first row, or maybe they won the second row. Okay, this is how we're doing it. We're checking if b11 is equal to the player, and b12 is equal to the player, and b13 is equal to the player, or all these other ways to win. Okay, hopefully that makes sense. Like the rows are all encoding the fact that either you won this way, or you won this way, or you won this way with your player variable. So that's how you can do it. And then you have your columns and then your diagonals, of course. You have 2 diagonals to check if somebody won. And so we assert that x won, and then o did not win. And then the way you make the sat solver like turn its gears and actually solve the problem is you say check sat and then get model, which shows you back the satisfying solution. Okay, so that is that, and let me show you this now. I've pasted it already in this website, so I can hit execute and it's going to find values for all of these variables that make it work. Okay, all right, so here's our model. It's like, okay, here's all this stuff. It made up some of its own variables, but this is how it works. It was very fast. So it does some tricks. So let's fill in the board that it found. That is its solution. Okay. So it's saying that b12, we're going to make sure that that is a 0. So b12, 0. That's an O. Okay. b13, that's an X. Okay. b32, that's a 1. 3, 2, that's an X. B21, that's a no. 1, that's a no. B33, that's an X. Ooh, some ways for X to win now. B23, that's a no. Oh, okay, so X maybe is winning this way. It has to, right? Then B1, 1, that is an X. Okay, okay. Ooh, X could also come over here. And then B31, that is an O. Oh, okay, so yeah, X won the diagonal. And then B22, that's an X. Okay, so this is its satisfying solution, where X won and O did not. And we can ask it to give us more by saying, I don't like this solution anymore, give me a different one. And that's how you can get everyone that exists in the world. So that is hopefully fun. That's a real-life example of using satisfiability to do something non-trivial, and it makes the search process a whole lot easier. Okay, so hopefully that was exciting, and let's move on now. So there's another way to simplify formulas that are written in logic. You can use your table, of course, but sometimes you would like a fancier method, like a bit of a graphical-based method, because we like to learn graphically sometimes. Okay, and the answer is this thing called a Kmap map, okay, or a Kmap for short. So I think that's how you pronounce it, Kmap, and we're just going to call it a Kmap in this class. What it is, it's a graphical representation of a Boolean expression that lets you simplify it very, very easily. It's quite nice. So instead of writing your truth table, like here's X and Y and 1 and 0 and 0, 1, and like here's all your other stuff, you're gonna write it in a different way. Okay, you're gonna write a table that looks a bit like this, depending on how many variables you have, of course, and this is going to really help you because you can start circling things that make it really easy to simplify things. Okay, and we like to simplify Boolean formulas because everything that every AND is an AND gate, every OR is an OR gate. Fewer gates, that cost less money. Yeah, it's very important. So instead of a truth table, we turn our expression into a truth rectangle, let's say, and we find patterns in it. Okay, so you're allowed to circle a group of ones or zeros. We're going to just deal with ones, I think. That's the easiest way. And the groups have to be of a power of 2 size. That's the rule. Okay, and also this rule for the Kmap rectangle that makes it work the way it does is it doesn't go in the normal order of like true true, false false, true true, false, whatever it is, true true, true false, there we go, etc., etc. We don't do that. What we need is that each adjacent cell must be different by only 1 bit. So if we're going to go from here to here, there must be only one thing that got changed. And that was, okay, A is false and B is false, A is false and B is true. That's the one thing that got changed right there. Okay? And so this now, true true, comes in the middle kind of because it's 1 away from A bar B because we took away that bar. And this one is 1 away because we added a bar to the B. Okay? So they're 1 away from each other, and obviously these are this 1 away from each other, 1 operation away, 1 flipped bit. And so here's our example rectangle, and if we fill this in with our formula, we can circle fancy things. Like if there are a bunch of 1s here, that's going to really help us simplify this formula. Maybe there are a bunch of 1s here. We can simplify it there and circle it here, and those can be our 3 groups. This one, this one, and this one. Okay, that's the idea. You can also do it with zeros and then negate everything at the end, but I think 1's an easier place to start for us. So let's do an example. So let's use a Kmap to fill in the truth values for the following logical expression, this one. And then we're going to use it to simplify the expression. Okay, we're going to find patterns, and I'm going to show you how to go from the patterns to the new expression, to the simplified version. Okay, so let's fill this in. A is false, B is true, and C is false. So we know C is false, we're somewhere over here, and then A is false and B is true. So this one, we're saying that that is true. Okay, it's true in that case, so 1 here. Okay, and I think you see how I'm going to go about this now. A is true, B is false, and C is false, a 1 there, and A is, let's see here, A is true, B is false, and C is true. So there's a 1 there, and then A, B, C bar. So A, B, C bar there. Okay, and then the rest are zeros. Okay, that's how you can go from that to just a truth table kind of thing. And the idea is we need to find patterns, okay? We need to write a simplified version of this expression. So can you find groups of 1, 2, 4, or 8, I guess 8's the biggest one, ones, okay? And we want the smallest number of different groups. Do you see it? So here's the answer. You got these guys and these guys. 2 groups of 2. And we can go from these to a solution by reading off what's the same about these. Like what makes these so special, okay? What is going on here that make ones in this spot, but nowhere else? And the idea is to look at all the things that they share, okay? And we want a 1 here, so we need to make sure that they share the same stuff, the right stuff. It looks like they always share C bar, so we can write that. C bar must be true for us to be over here. Then we need to figure out what's similar about these. Well, it's certainly not the A, yeah? But the B is true when both of them are true. Ooh, how about that? So B, C bar. You see that? That will make it true. Yes? And this is the game we play. Let's do it now to the other one. So, that is the point. Now let's do this one. What's true about all this? It looks like, oh, it's true when, well, we have no clue about what C is, because C could be anything, but we know that A is always true and B is always false. Ooh. How about that? Yeah? So let's see if this checks out. I'll use a different color. Here's the idea. Let us do this one. Let's make sure it's a 0 here. So A is false, and B is also false, and C is also false. Do any of these make it true? Like, no, we don't have it being true there, because it's only true if B and C bar are true. But unfortunately, we don't have a positive B, and similarly, we don't have a positive A as well. We don't have a true A, so we have to put a 0 here. And you can play this game all the way around. Like, for the same reason, you also have to put a 0 here, because there is no case where A bar is true. Okay, there's no A bar in any of these. So we have to put a 0 there. Why is this one a 0? Well, it's true. It must be a 0 because we don't see a C anywhere. We see C bar, but not a C. Okay? These all end up checking out for different reasons. And that is the idea. So this is how we can make sure that everything is right, and obviously these are going to be 1s because we have A is, we don't care, but B is true and C bar is true. So we're going to put a 1 here. Checks out. B is true and C bar is true. We're going to put a 1 here, regardless of what A is. And similar for these two, and it just all checks out. And this is the simplified form of this. And I think you see how much better it is. A times B times C, or, and some negations going on as well. All of those different tiny gates that we need to include to make this one happen. All we really needed were these. We needed 2 ands, 2 nots, and an or. Not too shabby, right? So that's a Kmap. Hopefully it makes sense how you do it. Now I want you to try it, okay? So give this one a shot, and then we'll come back and do it together. So, let's see what we have. We're going to fill in a Kmap with the following truth values, okay? So let's make sure to fill it in, and then we're going to find a simplified version of it. So we could copy it, but let's, for our own practice, let's draw it out. And you can pick whatever variables you want to go on all these rows. Normally when there's 3 variables, it looks like this. There's got to be 8 little boxes. And you can put whatever variable here you want, but I guess I'm going to put C and C bar. And we're going to do the same thing over here. It's going to be A bar, B bar, and then A bar, B. They have to differ. I could technically put A, B bar here if I wanted to. No problem. You'll get the same answer. And then this one has to differ and not be anything we've seen before, so it needs to be A, B. And then this one can be A, B bar. Yeah? That's the idea. And so now we just fill it in. So let's use blue for that. It's true if A and A bar are both true. That's never true, right? I don't think we can ever have that. So unfortunately, nope. There are no ones to fill in there. So that was a useless thing. You see that? Completely useless to have that there. It'll never be true that they're both true. Then when B is true and A are both true, we put a 1, regardless of what C is. You see that? And then when B is true and A is false, we put a 1, regardless of whatever C is. It doesn't matter, because this part will make it true. And then also, C is true and C is false. Woohoo! We can never have both of those at the same time. Again, that was useless. You see that? That's the point. So, watch this, because this is going to be really fun. You might think that the answer is get rid of those. Yeah? Let's put this here for posterity. You might think that the simplest form is AA bar, or sorry, the ones that aren't that, BA or BA bar. Yeah? But we can do better. ... Can you find a more simplified version of this formula? You need to circle, remember, the name of the game is circling groups of size 1 or 2 or 4 or 8. You have to find ones. Also, you can technically find zeros and do it the opposite. But you have to do it this way. You have to find a power of 2 things that are right next to each other. Maybe all in a line. Like they could be all in a line like this. Or they could be the whole darn thing. They can be any two, anyway, like this. That's fine. But they all have to be connected, okay? They can't be, you can't like start drawing Tetris pieces, okay? Has to be straight lines, has to be boxes, okay? Must be rectangles / squares, blah, blah, blah. No Tetris pieces. And probably wants me to capitalize that, sure. Why not? Okay, let's see if we can make this go down a little bit more. That works for me. Okay, here we go. Can you find a group of 1, 2, 4, or 8 things that are ones here? Find the biggest one possible. That's going to give you the best payoff. Okay, so I think you can find a group of 2 2s, but we can do better than that. All right, we can do this whole darn thing right here. Do you see that? Did you get that one? And then it's our job to figure out what's the same. What makes this part so special? What's the formula for it? The C's aren't helpful because they're different in this row and this row. So C can't be included here. Okay, what's so similar about these ones then? What's in common with this column and this column? It's certainly not the A's because the A's differ. Oh, but the B's are always true. And that is the story of how this long thing simplifies to just B. Do you see that? Isn't that fun? So yeah, that is using Kmaps. You're going to do this in your homework, so hopefully it's making sense. It's a lot easier for me to show you it than to write it down as explaining it. So hopefully these examples are going to give you all you need to do it right. So that's how you simplify things. You just look for what's in common, okay? And then you can go off and verify that it's all going to work. So that is Kmaps. And then one last thing that I'm not really going to test you on is just a taste of CSCI 45, in case you're not double dipping and taking it right now too. You'll be taking that next semester most likely. here is a fun idea. Here is how you can do math with logic. Okay, I promised you this. So circuits are cool and all, but what's the point? Well, our computers, of course, are made of nothing but giant, huge circuits all over the place. A bunch of transistors that encode and, ors, and nots. This one's an XOR gate, in fact. Does the XOR operation. And how do we make a real computer out of them? Well, it involves clocks, which we're not going to talk about in this class. And I didn't actually learn in my CSCI career. That's more of an ECE thing or a CE thing. Well, the other thing is, how can we use these logic gates to make computational processes? How do we add numbers? How can we represent that? Okay, that is what I will show you here. So I'll give you a little taste. This right here is called a half adder. It's not like a snake. It adds numbers, like add as in plus. Okay, add as in number plus, not or anymore. Okay, this is called a half adder because there's also a full adder. But the idea is, we notice this. Dun, dun, dun. We notice that the XOR operation, here is x and y and x XOR y. We notice that that is doing 1-bit addition. So 1, 1, or let's go back to trues. True, 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 false, false, true, false, false. XOR does 1-bit addition when you think about it. 0, 0, 1, 1. Yeah? Or true, no, sorry, false, true, true, false. Why is it doing that? There we go. Which is really equivalent to 0, 1, 1, 0. So 1 plus 0, yeah, that's 1. Yeah, 0 plus 1, yeah, that's also 1. 0 plus 0, yeah, that's 0. And 1 plus 1, you got to carry, but there's a 0 in the ones place. You see that? What? It's really adding. And you can chain these. You can do a bunch of XORs with a bunch of different binary positions, with a bunch of different bits. So the idea of an adder is, or at least a half adder, is it takes your two numbers, your two bits that you want to add, okay? Those are the bits that you want to add together. And this will represent the sum of those bits, like 1-bit addition of A plus B. Yeah, that's what sum will give you back. If you do XOR on A and B, it'll give you the sum. And then also, it's possible that you need to carry, because if you did 1 plus 1, yeah, it's 0, but really it's 2. So we got to carry that 1. And here's how you do it. You bring the carry out in a different bit. Okay, you just make sure, okay, did I carry 1 or 0? Yes, I did. 1 if we need to carry. So let me show you this working on the next slide, and that'll be that. And you can have a full adder. You chain a bunch of these together is the idea. You put them one after another. You have a bunch of little bits. So you're adding a bunch of numbers in binary form. I think I added an extra bit, sorry. But the idea is it goes 1. Okay, we got a carry. And you just funnel these bits along, and the carries along from right to left, and then you have the sum down here. That's the beauty of it. Okay? So let me show you this with like 1 and 1. So let's pretend this is a 1 and this is a 1. Then 1 XOR 1, that's a 0. But we notice that these are both 1, so we AND them together, remember? And this will give back a 1 so that we need to carry. Okay? And let's do it one more time for like 1 and 0. Why not? Whee! So instead of 1 and 1, we'll do 1 and 0. And add them together. XOR gives us back a 1. And then we don't need to carry because we stay in the same place. Okay? 0. And the idea is you kind of like chain these along. It's like, okay, there's now a third bit that you need to add in a full adder. And so you kind of like give that to that, if that makes any sense at all. A full adder needs to bring along the carry. Okay? So that's my fun taste of CSCI 45, and that brings us to the end of these slides. So hopefully that wasn't too bad. It's Boolean algebra. You know a lot of it already, And yeah, hopefully you learned some fun stuff here. It's a fun set of slides to teach, I think. So I think that's all I have for you. There will be a new homework because of this, and just keep that in mind. And I think that's all I have for you. So I will see you next week.